like for my
Just take all three. I mean, you just have to pass three.
right.
So just take all three.
Yeah, that's I also misread that. But yeah, it's annoying because I have to be in that group for a weekend and then like a week after, not even during the weekend, I have to fly back and be there for like 2 days. And then
Okay. So. Okay, so last time I spent a certain amount of time trying to draw the parallel between what we've seen so far in the setting of generative linguistics and the model of merge, and what had been happening before in theoretical physics, in modeling perturbative quantum field theory and the renormalization process in perturbative quantum field theory. There's a kind of in-between step between these two manifestations of the same kind of mathematical formalism. And this is something that happened sort of in between these two other things that I've been talking about. And it's something that around 2009, 2012, Yuri Manin was working on, which is a proposal for trying to adopt the same formalism that we've seen in the quantum field theory, in the perturbative quantum field theory and the problem of renormalization in the theory of computation, where you basically want to think of certain kind of known computable functions or problems that are unsolvable for logic reasons as being the analog of the infinities of the divergences of Feynman integrals in quantum field theory, and try to adapt some of the same formalism, try to understand when it is possible to extract some sub computations that are actually computable from a possibly non-computable problem. So I'm just gonna quickly give a very brief heuristics about what this was about, so that in a sense one can see how it's a sort of problem that shares parts of both the physics and what we've seen in the linguistic setting. And so the idea is to treat non-computable functions like the infinities of quantum field theory, that what in the physics theory of renormalization corresponds to extracting a finite part, like a meaningful physical value from divergent Feynman integrals, would correspond here to extracting a computable part from non-computables. So again, one sort of models this with the same idea that you separate out two parts of the structure. One of them that takes care of the underlying combinatorics and is modeled by some kind of Hopf algebra. And another one that takes into account the values, and it's somehow the place where you do the checking and when you do the separating out of the parts that you want to keep and the parts that you want to throw away. So in this setting, the Hopf algebra represents some schemes of computation. So something like flowcharts of computation. We'll have, I'll show in a moment more precisely what that corresponds to. And the analog of the Feynman rule with values in a certain Baxter structure where you can separate out infinities from things that are convergent would be where you check the presence of non-computability. Okay, so in this case, this is something that I've already mentioned a while back when we were talking about formal languages and the type 0 grammars. So you have a class in the theory of computation. You have a class of primitive recursive functions. These are the actual computable functions that are they have a presentation in terms of generators and relation. There are certain basic functions, the successor functions on the integers, on the positive integers, the constants and projections, so that you can have higher dimensional things. And you have elementary operations that puts these basic generating functions, generators of recursive functions together. One of them is the fact that you can compose them. Another is you can bracket them so that you can form vectors of functions. And the most important one is that you can define things, construct things that are defined recursively. So composition, yeah, is just composition of functions. And as I said, bracketing is just the possibility of forming vectors of functions. And the important thing is the fact that you do have a recursive algorithm, which comes from beyond arithmetic, the fact that you have recursion in the arithmetic of integer numbers. So the point is that anything that is obtainable by starting from these very simple building blocks and applying any of these operations in an arbitrary way is what you consider as the primitive recursive functions. Because you can give other characterization and show that they are equivalent to this one. This one has the advantage of being these explicit generators and relation kind of presentations. So the idea of what you want to have as a kind of combinatorial models in this setting of renormalization applied to the theory of computation is something where you have planar rooted trees, which represent your computational charts, your kind of flow charts of your model of your computational process. And these are labeled in such a way that the vertices can be labeled by one of these kind of elementary operations that you do. And the edges or alpha edges are labeled by some of these primitive recursive functions. So it means that your one of these charts, one of these trees, is an algorithm for assembling together some of these functions according to a specified choice of these operations that you perform on the elementary building blocks. And of course, these have labeling have to have some admissibility in the sense that these operations have a certain number of inputs and outputs, and you want the valence of your vertices, the branching of the tree to correspond to the number of outputs that you have for the given operations. So the labels cannot be assigned arbitrarily; they have to be assigned matching the shape of the tree. And the operations that make this Hopf algebra are exactly the ones that we have used already several times. The product is just the one that gives you forest, where you have some independent parallel computations that don't mix inputs and outputs. And the co-product is the one that extracts subtrees and contracts the corresponding remaining part. This is going to be non-commutative, and the reason why you want to take planar trees and the non-commutative algebra is because some of these operations, or this bracketing operation, have an ordering. They are actually ordered sets of functions, so you need to keep track of order. And you can also reduce your trees to be binary, because your bracketing can always be composed of binary ones, or repeated iteration of binary ones. And so this can be formulated either in terms of these larger concurrent of algebra of rooted trees that has trees of arbitrary order with valences of arbitrary orders, or it can be reduced to things that can be expressible in terms of binary trees. And so far, I've only mentioned these total recursive functions, which are actually, so there's nothing that has computability issues in that class, but one can extend this, as we have discussed already once before, to this larger class of partial recursive functions, where you have some kind of I mean, these are again given by explicit generators and relations, which include the ones that were we had before, but it includes an additional operation which now has this issue of domains. So the point of this is that you want to take into account, so you want to have not just the computable functions, but also the ones that are semi-computable. So it means that you have an algorithm that will, output the value of the function at all the points that are in the domain of the function, but that will never stop if you are outside of the domain of the function. But of course, the reason why this gives you non-computable things is because deciding whether an algorithm stops or not on a certain input is an undecidable problem. So this means that there is this allows for incorporating undecidable problems into your set of functions. And so this you can incorporate in the same of algebra formalism by introducing this additional generators of your computational structure. So these additional vertex type of vertex. And so the idea then was that, okay, you can hook up certain kind of characters for these off algebras, which take values in some space of analytic functions, for example, that's your target, and that will detect the difference of whether you have one of these domain problems or involved or not. So, for example, by the presence of a pole or not. And in particular, this means that if you think in terms of what we've seen as this Birkhoff factorization, where you take into account not just the function itself, but the overall tree that computes the function that you're computing, but also all the substructures and all the sub functions that are building blocks of your of the one that you end up with, then this might allow you to show that where your infinities or your non-computability are located inside the diagram that computes your design function. In particular, you have phenomena where you can either have you can have sub functions of these sub computations that are non-computable, or you can have the overall thing being non-computable, but sub actually that are computable. So it allows you to better keep track of all the substructures at the same time through this factorization matrix. So, and yeah, so for example, this is something that happens here that one can observe, which is a bit different from what happens in quantum field theory, is that in quantum field theory, if you have subdivergences, if you have sub-diagrams that are already divergences, then your entire Feynman diagram is also divergent. But with this, in this setting of serial computation, you can have cases where your overall diagram gives you a computable function, but there are substructures that are non-computable, and this will allow you to identify where they are. So this is a kind of interesting direction of application of these ideas on quantum field theory, which, well, by and large, still, I think there's a lot of things that are interesting to explore into this question that have not yet been looked at. But in a sense, I wanted to mention it here because, well, partly because it's an interesting problem in itself, but also because, in a sense, this was like an intermediate step between, thinking in terms of the theoretical physics and thinking in terms of linguistics, which is a form of computation. In a sense, that's what was the whole point, that the structure of syntax in generative linguistics is a form of computation. And so this is kind of already suggesting that these tools from physics were also suitable for thinking about problems that have to do with computational structures. Okay, so this was like the intermediate kind of history, how things were going from the physics to the linguistic application. And so I wanted to go through that first because I think it sort of explains better where the main ideas are coming from. Now, the next thing that I want to talk about, which is how one uses this kind of yeah, so one uses this kind of idea to give a model of how the computational process of syntax interfaces with semantics, or know how structures can be parsed for meaning, and how this is related to syntax as an abstract computational process. So this is actually like this third part of these papers that we were writing last year, and this is also included in the book. So the way this was formulated in Chomsky's Merge and Strong Minimalist thesis book is that you have this original mechanism that computes syntax that starts with lexical items and syntactic features, assemble them together in the workspace, has this merge operation that acts on the workspace and builds structure, in this completely free way, and that includes structures that are not viable. Well, first of all, they are not viable for things like heads, theta roles, and this kind of additional structure that we've been discussing, which are already prior to externalization, in the sense that there are still concepts that are common to all languages, but also then some of the structure will be viable or not in specific externalization, specific languages, depending on syntactic parameters and so on, as we were discussing before. So there is this central computational mechanism, and then on one side it goes to this externalization process that manifestly embodies it in the particular language, and it also has to do with how language is then translated into speech or writing or something that's externalized, and that has to do with our sensory, the way our sensory motor system works. And on the other hand, there is this what they call this conceptual intentional interface, which is the one where parsing for semantics happens. And so in the model that they're describing, these two interfaces are to a large extent independent, in the sense that so this is the point of view of language, the I language as it is formed and then externalized. And so in a sense, there are two roles, right? We are both generating languages, and we are receiving languages and parsing it. So this is the point of view where you are generating language. So you are generating structures and then passing them through some filters that have to do with specific externalization and have to do with semantic parsing. And from that perspective of being the generator of language, these two kind of filters can be regarded as, to a large extent, independent of each other, in the sense that semantic parsing can happen independently of particular embodiments into particular languages. I mean, the history of linguistics, this is sort of an interesting controversy. There was this whole idea that was called Sapir-Whorf principle, or strong Sapir-Whorf principle, where people were trying to argue that specific languages that you speak make the semantics different. I mean, the things that you're allowed to express in a certain language are different from the things that you're allowed to express in another language. And of course, there were supposed evidence for this, and a lot of the evidence over time was debunked. And it's by and large, people don't believe this Sapir-Whorf idea. I mean, it's good for science fiction movies. That's Arrival is like a strong Sapir-Whorf based idea, but it's not considered. So, and this has partly to do with this idea that the channel that goes to the semantics interface is by and large independent of the channels that goes to the externalization in specific languages. This formulating the model like this is is like a strong rejection of the Sapir-Whorf principle. There are no things that your mind is not capable of expressing in any arbitrary human language, because the part that expresses meaning bypasses which particular languages you will end up using for doing that. So that's part of that. Okay, so of course, in a sense, this picture needs to be enriched a bit when you think of language being at the receiving end of language, because of course, when you listen to a sentence or read a sentence, you are parsing something which has already gone through the externalization channel. So if when you are at the receiving end, your interface with semantics is intertwined with the externalization because you're receiving something that is already presented in that form, right? So because when you're talking about parsing, things are a little more intertwined than this. And I'll be discussing that later. So now we're gonna try to see like how one formalizes this picture in terms of this model that I've been discussing so far. So far we are up here. We have pretty much given the whole picture about how this model of merge functions at the level of the free symmetric merge. And then, I've been discussing, a bit also how the externalization procedure works. It has two types of operations that happen. The plenarization of trees that fixes the word order of particular languages, and filters that will take into account other constraints on the syntax of particular languages that single out certain structures as viable or not. And I'm gonna talk about what happens on this side now. And then, of course, because as I said, when you are, so the point of view here is now going to be both the side of, in which you are generating language, but also the side on which you are parsing language. And one of the interesting points is that, it's because this is the central computational mechanism, right? So this should be responsible for both things. It should act both as a structure formation process and as a parser at the same time. But that's the same, so it should be the same core mechanism that does all the computational work, both when you produce language and when you parse it. So the same algebraic structure here should be responsible also for parsing. But I mean, for parsing, there's something else that has to come in, which is this interface with semantics. And this, as I said, these two things are eventually have to be combined, because if you're doing parsing, you are dealing with information that's already being externalized. And I'll show what these various pictures actually correspond to in this different channels. Okay, so how do we formalize the interface between syntax and semantics? So first of all, semantics is a big quagmire whenever you get into linguistics. There's nothing about which linguists have been fighting with each other more than about semantics. It's just like a lot of different ideas or models of what semantics should be, and which have been highly debated over the years. So I want to take a point of view here, which is as minimalistic as possible about what you assume on the side of semantics. And I think there are good reasons for trying to do this, because if one thinks again in evolutionary terms, as I was saying several times, language is a very recent acquisition in evolutionary terms, and it emerged in a very quick time in the evolutionary scale. So most of the mechanisms that language relies on have to be things that were already available for other purposes in our brain. And so the idea about the most essential model that you can build is something where you have like a single additional mechanism, which is this computational mechanism that we have described, but everything else is sort of piggybacking on things that already exist for other purposes, like other kind of functions of the brain, vision, and other kind of conceptual or perceptions and conceptual evaluations of perceptions. So in a sense, this point of view is sort of trying to show the following thing, that even if you take the minimal possible assumption about what you have on the side of semantics, you can still do some reasonably good computational model of parsing in semantics. This doesn't mean that you cannot enrich the side of semantics with other things, and I'll discuss how one can do that. But I'm saying that even if you don't, you still get something that's viable enough. And of course, this really gets a lot of people who work in semantics not particularly happy because they actually like the additional structures that you put on the side of semantics. But I mean, I'm not saying that they shouldn't be there. I'm just saying that you can also do something where you don't assume that much. Okay, so we're going to take these basic requirements about the interface between syntax and semantics. So the first one is what Chomsky calls autonomy of syntax. And this means that the generative process, the computational generative process of syntax is completely independent of semantics. It acts on its own. It's like this thing that bubbles up structures, and generates them regardless of whether they will be viable or not for semantic parsing. So it just acts on its own, and it would act that way regardless of whether the semantic interpretation functions or not. And the second principle is that syntax supports semantic interpretation, and this is what I also call a syntax first view of the interface between syntax and semantics, which means that the interface proceeds from syntax to semantics, and it's syntax that drives the way that the semantic parsing should be done. And I'll explain more precisely in what sense I mean this, but essentially it is say that syntax puts together structures, and semantics has to be modeled on, the semantic parsing has to be modeled on the way that structures are built together, assembled together on the side of syntax. And so the other principle is this fact that I mentioned a moment ago, that semantic interpretation is, at least to a large extent, independent of externalization, at least when you produce language. And the last principle is compositionality. So that basically what I mean by compositionality is the requirement of consistency across substructures that semantic parsing is going to build bottom up in the same way as the structures, the syntactic structures are built bottom up. Okay, so let me make another basic principle for modeling syntax and semantics, and this is exactly where I'm saying. So this is a way of saying that I'm assuming as little as possible on the side of semantics. So I'm going to put all the computational work on the side of syntax. So syntax is a computational process, and semantics is not in this model. So what is the minimum that I want to keep for semantics? I want to keep some kind of topological structure. Well, what I mean by that is that what I want to be able to do on the side of semantics is comparing things and being able to say when something is similar to something else. So if two things are near each other, is having a way of measuring distance, maybe. So something could be not just topological about metrics, but anyway, things that are topological in nature, in the sense that they have to deal with proximity relations between. And this is in a sense coming from this idea that whatever kind of conceptual spaces, semantic spaces we use for language parsing, could be things that already existed for other purposes. For example, if we parse images, right, the most important thing that happens when we parse an image is that we have to decide what goes together with what. Right? If we are observing a visual scene, one of the main problems is this contour problem, like what is together with what? What is part of the same object? What is two different things? What contours are like accidental and which are actually real, with things to separate out different elements of your visual scene. So it's mostly, if one thinks about what are the kind of conceptual spaces that are studied by neuroscientists to look at other kind of perceptions and how we process those perceptions, they're very often based on this idea of trying to decide what goes together with what. And so it seems like a reasonable assumption that at the very basic, what we need to have on the side of semantics is something that does this kind of things, that where you can keep track of what goes together with what. So we can take this very basic model, like computation is coming from syntax, and topology, proximity is coming from semantics. Okay, so these are the basic assumptions. And now, okay, comes this idea of trying to adopt what the formalism that was used in the setting of theoretical physics to model something like this. So let's assume that you have, to begin with, a certain way of assigning to lexical items some corresponding values in some semantic space. This, of course, is a reasonable assumption, because when we learn a language, one of the things that we learn is to associate words to certain concepts. And so we can think of, in this sense also, you can see that it does make sense to think of semantics as an open condition, because you assign a concept to a word, but that concept is more like an open neighborhood rather than exactly a point, because you expect that concept will vary slightly according to where the context in which that word occurs. It might vary for different people if you're trying to compare a shared kind of semantics for the same words. So one can think of this assignment of semantic values to lexical items as being a map from your set of lexical items and features to some semantic space, which will have some kind of topological structure. And now the question is, you want to actually be able to parse, not just assign concept to words, but you want to be able to parse sentences. So since you want to extend this map to to syntactic objects rather than to lexical items, you want to assign parsings to completely formed structures, not just to individual lexical items separately. And you want to do this in a way that has this property that I just described, in particular that it has this compositionality property, so that whatever values you assign have to have some consistency over the substructures in your syntactic object. And so here is where this idea of that's used in theoretical physics. The idea there is that you want to incorporate all the checking of substructures into a single function. That's what this recursive formula for this factorization that I showed last time was actually doing. It was, instead of just taking when we were evaluating, we were showing how to evaluate this the Feynman values, Feynman diagrams, and normalization. You assign your regularized value not just to the graph itself, but to all the subgraphs and the corresponding quotient graph in a single expression. And that's the consistency checking over all the substructures built together into a single object. So it means that maybe a good way to keep into account this consistency, this compositionality that you want to have, is to do a similar process that builds this checking of substructures into a single map that will be the extension from the lexical item to the structures. Okay, so this is the idea. Okay. And so what one needs to implement this idea, I mean, seeing how the formalism works in the case of physics, is two ingredients. One, this is exactly the same, following the same model that we've seen both in the case of physics and in the case of computation. That you need a combinatorial side and like a source of and the target of your Feynman rules. There's a combinatorial structure at the source, and there is some measuring structure at the target. And so the combinatorial structure at the source, the purpose that it has is to extract substructures and present for you the list of all the possible structures and the corresponding quotient structures, so that you can do this consistency checking. And what the target space is supposed to do for you is giving you a way of separating out agreement and disagreement. So being able to distinguish like the part that you want and the part that you don't want in the case of Feynman diagrams, so convergent part and divergent part. But in the case of semantics, would be like matching what agrees with what and what disagrees with what. So this is the idea. And as we know from the case of the theoretical physics and the case from the theory of computable and non-computable functions, the first operation, the extracting substructures and quotient structures separately, is done for you by the Hopf algebra structure. It's the co-product of the Hopf algebra that does exactly this work of breaking up things into substructures. And what happens at the other side, this filtering of agreement and disagreement, is actually what is done by this Rothe-Baxter structure that is used in the theory of renormalization. And in the case of physics, we have seen this Rothe-Baxter structure in one particular example, which is the one that's usually adopted in physics, which is Laurent series, where the Rothe-Baxter structure is the projection that takes on one side the divergent part and on the other side the convergent part, and separates out these two. But we're going to see here that the main role here of this Rothe-Baxter structure is to allow for some kind of filtering. And the point is also that if you think about it, that's something that you need, because if you want a good model of semantic parsing, you're going to have some kind of degree of agreement or degree of disagreement. Of course, in the coarsest kind of picture, it could just be a Boolean value. It's either 0 or 1. It's okay or it's not okay. The parsing works or the parsing doesn't work. But most likely, it's something where you can say that there's a certain amount of agreement or a certain amount of disagreement, or a certain likelihood that this parsing works or not, and you can have a threshold for how much agreement or disagreement you allow. And so you want to be able to do your parsing as dependent on some kind of threshold that would rule out the things that have like too little agreement, for example, or a too low a probability of working. So in this setting, these Rothe-Baxter identities, I will show in a moment, will play that role of being threshold functions. So, and in particular, this picture is compatible with what I just said, that it is the same mechanism that is responsible both for the structure builder and for the parser, because it is, in both cases, the coproduct of the Hopf algebra. It's the one that allows you to do these movement kind of operations for structure building, because it extracts substructures that you use for internal merge. But it's also the same thing that allows you to do parsing at the same time. So it is the same computational mechanism that's responsible for both things, as one expects that it should be. So you don't have to like introduce another completely separate mechanism that takes care of parsing. It's the same that does structure building that also does parsing. So let's just take a very simple example, and we can see what I mean by consistency over substructures. Okay? So suppose that I take these sentences. I take the sentence of France is a republic, France is hexagonal. That's all uncontroversial parsing of what they mean. But if I put them together and I say France is a hexagonal republic, this sounds kind of funny, right? It's not like it's not parsable, okay? It's not like it, but it sort of sounds awkward. And the reason why it sounds awkward is because we generally agree that a polygonal shape is not a property of a form of government. And so what is going on here? Okay, if we think what is this syntactic object? No, you can write it. Well, you can write out the tree if you want. This is like with the set structure, where these are your various lexical items. And now, if you start to break this structure apart with your coproduct, you will end up with terms in your coproduct where all the pieces parse uncontroversially, and you will also isolate certain terms in the coproduct that exactly contain the pair that is creating trouble. So this is a very simple example where you see that when you start to parse the structure, you will have substructures that parse without encountering any issues, and you will have certain particular substructure on where the issues are actually located. And the idea is to that the parsing should exactly take care of telling you what works and what doesn't work, and where exactly what doesn't work is located. Okay, so let's then try to come down to what are the basic building blocks for what you want to have on the side of semantics. What are the basic properties? So as I said, the main property that I want to have on the side of semantics is something that will allow me to say what goes well together with what. Right? So I can think of having a certain space, which is a topological or maybe more generally a metric space. And for example, one good property that makes sense to require is that you have some form of interpolation there. Because you would expect that if you have for example, if I give you a noun and then I modify it with an adjective, I could think that this structure will correspond. My noun is associated to some point in my semantic space. When I modify it with an adjective, I'm sort of pushing this point a little off into some direction, which is in the direction of where this other point, I point for all my lexical items to begin with, so I'm sort of pushing a bit in the direction of the other point. So if I have some way of doing interpolation between points, this is capturing this idea that meaning can be slightly modified by modifying my word in the context of some syntactic structure. And so, for example, I could say if I want a kind of model that has all of these properties, I could say, if I have some Riemannian manifold, which is geodesically convex, then I do have always paths between points, and I can always interpolate, and I have neighborhoods that I can decide how much overlap I have between what I can measure distances, and so this could be like a fairly rich model of what I can put on the semantic side. And there's something else that I want, as I said, is some way of assigning agreement and disagreement. For example, with respect to some probe, I can say I want to see how close this is to a certain particular semantic probe, some particular point. Am I close to that point? Am I not? Or am I in agreement or in disagreement with a certain hypothesis? And so this is where this Rother-Baxter structure will come in general. So in physics, one usually takes the target of your Feynman rule as being an algebra, like the algebra of Laurent series. In linguistics, one usually works with things that are more like semirings than rings, in the sense that they're often things related to probabilities and things like this. So you want sometimes some kind of positivity and some kind of convex combinations rather than just combinations. So there will be, I will show it in a moment. There's a slight modification of the algebraic structure of Rother-Baxter algebras, which applies to semirings, and you can think of your target as being a Rother-Baxter semiring. And you want probes, so ways of saying comparing agreement and disagreement with respect to some hypothesis. So these are like the main picture of what I'm gonna put on the semantics side. And so I'm just gonna pretend that everything is flat. So I'm gonna write the geodesic arc between 2 points just as a segment, for simplicity. And if you want, I can keep track of comparing things. For example, like two simple ways would be to have something like a probability that is measuring like the degree of agreement between 0 and 1, and or something where you want to also assign that tells you, agreement and disagreement and amount of that, which is more like a cosine similarity. For example, if you have a vector space model, like these vector space models of semantics that are used in computational linguistics, you can use the cosine between two vectors as a way of measuring agreement or disagreement. So you assume to have like some comparison function that is built in this way, either as a probability or as a signed side measure. And so, right, so this just means, what I was saying, that this kind of properties here are pretty independent of the fact that this is going to be used by language. Is something that could very well be a model of conceptual spaces for other purposes. For example, there are models of conceptual spaces for vision that are used by either people working in neuroscience or people working in computer vision that have exactly the same kind of properties that I just listed. So it's some way to keep this compatible with what can be used by other functions of the brain that are not language. Okay, and so so there's a bunch of other situations, like for example, as I said, there are results about perceptual manifolds which are about vision, which is kind of based on the same principles that I was describing. And there were other models for semantic spaces for language that are also have a similar picture. And Gardenforth, these two books about models for semantics for not just for language, but in general for thought or conceptual spaces for thought that are also based on this idea of convexity, interpolation, and open neighborhoods, overlaps of open neighborhoods, and so on. So I think this it fits in a setting which is quite general. So okay, now the next step is how one proceeds, assuming that you do have this kind of assignment of semantic values to lexical items. So this will be something learned. As we learn words, we sort of learn this map on from lexical items to semantic space. And then there will be something that is actually computed rather than learned, which is how to extend that map to syntactic objects that are not just single lexical items. And one can assume that we have already filtered our syntactic objects by eliminating those that are non-parsable. For example, those that don't have a well-defined head function for the structure. So, there are these filters that are prior to externalization, and they would be prior also to the syntax-semantic interface. So things that are not filtered out, that go to the interface with semantics, we can assume that are already checked for being parsable in terms of head complement, specifier, theta roles, and things like this. So all of this structure is already checked that works consistently. Okay, so well, one thing that you can do, I mean, in a sense, the simplest basic model that you can do at this point is, okay, if I have a structure that has certain lexical items at the leaves, and I know where my lexical items are mapped in semantic space, and I know that I have geodesic arcs that interpolate between them, I can say that, okay, when I'm putting these two structures together here, I'm connecting them by some geodesic arc here. And so the place where I'm gonna place the, let's say the root of this tree, which means in a sense what corresponds to the entire structure, would be some point in between these two. And where I place it, well, this is kind of gonna depend on some of these additional structure. That's the reason why I'm saying that you, for example, want to have a head function, because a head function is telling you of these two elements, which one is like the most important one. And for example, if I am taking a noun and I'm modifying it with an adjective, I assume that I'm kind of near where my point was, where I'm mapping my noun, and at least in it is a first model approximation. What I'm doing is I'm just slightly pushing off this along the direction of this other modifier. And how much I push it off, right? That might depend on what these measurings are like. Like if these two have a strong contrast with each other, then I'm pushing it off by, a lot more, because, I'm sort of making something that's, expressing a contrast between two. Yeah, but if they are very closely related, then I expect to be pushing it off very slightly. So, of course, this is like a very simplified model, but I'm trying to describe like what is the minimal kind of thing that you can expect. So this is going to give you something that will work. So you have then if you add another piece of structure, maybe that your construction goes bottom up. So this structure is completed first, and then you add in another one, which would mean that now you are somewhere in between these 2 points in your semantic space, and you are again, connecting that point in between with a geodesic arc with the other thing you use to modify it, and your new point that corresponds to the root of the structure will be somewhere along this arc. And in particular, this sort of gives you a mapping of the syntactic objects inside semantic space, which is in general going to be an embedding. It might not always be an embedding, but in general it would be an embedding.
Question.
Yes.
So is it right to say that S is always indexing the points in the semantic space, or can it index extended objects?
It will index extended objects in the sense that you do have an image of the tree, right? Because if I have the image of the leaves, but I also have the geodesic arcs between them, and I have where my root vertex is going to. So I have the arc from the root vertex to the other leaf, and some place where I'm putting the root vertex here. So I'm effectively embedding my extended one-dimensional objects, my syntactic objects, as embedded trees inside this semantic space.
But in the function there, you wrote the set of lexical items. So you're saying that it can also index the trees or the forests.
Yeah, in the sense that you can assume that the image of the lexical items is like what is learned, right? And in the sense that is part of the learning process that associates concepts to words, but then you compute like where the rest of the structure, the extended structures are mapped. And I can say, for example, that I can, well, the only thing here that I actually, for example, if I take this subtree that only has alpha and beta, right? And I know where alpha and beta go to 2 points here. And so I know the geodesic arc between these two, that's already given. The only thing that I need to know is where the root goes. So which point on this arc is the one that would effectively represent this entire structure, because the rest is just determined by alpha and beta. And this one I can compute on the basis of these functions that measure proximity or similarity or contrast in my semantic space. And that will compute an embedding of the tree. So this will give me so the same semantic space will contain not just an image of the lexical items, but it will contain an image of the syntactic objects. I mean, at least those that have a head that one can use to make this computation.
Okay.
Okay, so this is like the picture of the geometric aspects, the geometric topological aspect of the semantic space. And now let me say something more about these Rothe-Baxter structures. So the example that I was describing last time that comes from the physics application is this notion of Rothe-Baxter algebra, where you have a commutative associative algebra and a linear operator on it, which is this kind of projection, right? That separates out R in the algebra R into two pieces. But no, the point is that it separates it out in such a way that the two pieces are, so the operator itself is just a linear operator. But no, it splits out R into two parts, which are not just subspaces, but they're actually subalgebras. And the reason why they are subalgebras is because of this Rothe-Baxter identity that shows that if I take the product of two elements that are in the range of R, it's also something in the range of R. Okay. So this and the weight -1 here is the one that reflects, for example, the properties of Laurent series as I was describing last time. And it is the weight -1 is actually what you need for this recursive formula for the Birkhoff factorization that I described last time in the case of renormalization to work. So there's a slight difference in formulation here, in the sense that factorization works for either Rothe-Baxter algebra of weight -1, so this is the sign of the -1, or Rothe-Baxter algebra weight +1. The difference between the two is that in the case of weight -1, when you factor out a character of the off algebra, you factor it as something which is phi minus composed with the antipode of the off algebra, product with phi plus. And if you use a Rothe-Baxter algebra weight +1, the thing would be that you can move that point term to the other side, and this would correspond to splitting out something that says that phi plus is phi minus times phi. It would just, and so if you write it in this form, that phi plus is phi minus times phi, you're not using the antipode anymore. And this means that this form you could actually still make sense of in something that is a bi-algebra, but not a half algebra, because you never use the antipode. And but the actual factorization, the form of the actual factorization will look the same. Okay, so as I said, in this setting in linguistics, usually people want to use semirings for parsing rather than algebras. So you can modify this notion of Rothe-Baxter algebra to Rothe-Baxter semirings, where now you have a pair of operations, sum and multiplication in the semiring sense. And the difference between the case of the algebra of the ring and the semiring is that now the addition does not have inverses. So that's what you lose, right? In the sense, you should think of it as, for example, if you have a ring and you take only things that have positive coefficients in your basis, that would be a semiring, because the properties, the relation between addition and multiplication, all the other properties stay the same, but the addition no longer has an inverse. Okay, so in fact, this is exactly why semirings occur, because you want things where you have some positivity of coefficients or some convex combinations or something where you don't have inverses. So the idea is that, okay, the issue now is that you're not allowed to do minus something, right? So it just means that a Rota-Baxter structure of weight -1 in the semi-ring sense, you can only write it with this term on this side. You cannot move it to the other side because there's no additive inverse. And the weight +1 is written exactly as you have it for others. So this is the only difference. Otherwise, everything goes through to the semi-ring case. And the main point that I mentioned already is that what these Rota-Baxter identities for semi-ring reflect is the idea of something that's like a threshold operator. So let me give an explicit example. So this is one of the main threshold operations that are used, widely used, is the prelude kind of threshold, which is 0 or the identity. And so if you take as the semi-ring, the tropical semi-ring is the one that has the max plus, also called max plus semi-ring, where the elements are the real numbers and minus infinity. Minus infinity is the additive unit. And the addition operation is the maximum, and the multiplication operation is the usual addition of real numbers. This is a semi-ring, and addition is not invertible. That's it's the maximum function. And so now I just verify that this is a linear operator in the semi-ring sense, and it is a Rota-Baxter operator of weight +1. So if you want to, so this is what you need to verify, right? This is the Rota-Baxter identity of weight +1, right? Let me just go back to writing it in this form. You want to say that the semi-ring product of the images is the same as this combination with the semi-ring addition of this operation, where you either apply it to either one or the other, and then you apply it again to the product, or you apply it to a product. So if these are our addition and product, this means, and I write X plus for this ReLU threshold, then this is the product of the images, and these are the three terms of the Rota-Baxter identity. So, okay, one can just compute what all these terms are, and you have to make the different cases where both terms are negative or no positive. One of them is negative and the other positive, and both of them are non-negative. And in all of these cases, you can see that this term is the maximum of the other three. So this satisfies the Rota-Baxter identity. So you see that this is kind of the behavior of a threshold function. You give another example. Well, there's a trivial example, which is that the identity is always a Rota-Baxter operator of weight -1 in a trivial way. And so if you are in the Boolean semi-ring, you don't have room for any other threshold because the only other threshold will be that everything is 0, right? So the only threshold that you have is the identity, and so that is a Rota-Baxter structure of weight -1. And the more interesting thing is where instead of having Boolean values 0 and 1, you have an interpolation. You have values between 0 and 1. So you have this case that's called the Viterbi semi-ring, or the probabilistic semi-ring, where your numbers are, your elements are numbers between 0 and 1. And you have the maximum as addition, but now you have the product as multiplication. It's not like the max plus semi-ring. And so 0 and 1 are the units. And now you see that another example of a Rota-Baxter structure for the Viterbi semi-ring is exactly, again, something which is like a threshold. So if you are below a certain threshold, it's just X, and if you're above threshold, you cap it off at 1 once you reach the threshold. And this is a Rota-Baxter operator of weight -1. And again, it's the same verification. You have to show that this product of the threshold is the maximum of this. So you just, again, have to do the various cases where something is above threshold, both terms are above threshold, one is, one not, and so on. And you get that the Rota-Baxter identity is verified. And so one thing that one needs to pay attention to in terms of using this Rota-Baxter structure to do factorization of characters is that if you are in the semi-ring case, because you're not allowed to move, coming back to this way, if you are in the weight +1, it will just give you that kind of factorization that I said, 5 plus equal, 5 minus times 5. If you are in the weight -1, because you're not allowed to move this term to the other side, you have to keep track of what is the maximum between these two terms. And there's an additional condition that you need to require for this factorization to work, which is that the maximum between these two, or the addition, depending what the addition is in your semi-ring, is actually equal to always to this term. And so this actually works well for the examples that I showed here. So in general, this kind of Rota-Baxter operators that are threshold will satisfy these properties. So this is just an algebraic property that describes the behavior of threshold on your evaluation semi-ring. Okay. So these are like two of the three aspects that I mentioned. What is like the topology interpolation structure, and what is this measuring threshold of agreement disagreements, which is this type of Rota-Baxter structure. And the other thing that I mentioned I want to have is some kind of probes that I can use to measure relative agreement or disagreement with respect to some hypothesis. And so, for example, one can take just to make an example, right? If you are, one type of space S that has the kind of properties that we want, convexity, interpolation, and so on, would be a vector space. That would be, a very simple example of a kind of space that I can use as target. So if S is a vector space, then, for example, I can have probes that are specific vectors in my vector space. And I can use those to say, I want to check how much agreement or disagreement I have with one particular probe. And so then, the corresponding measure of agreement, disagreement will just be, for example, the inner product with my probe vector. And so, for example, I can form a character, of my Hopf algebra of workspaces by assigning to some forest with leaves decorated by my lexical items. I can assign to them values, which are basically just checking the agreement with a particular probe. So there will be a character for each probe that I want to use, and that character will check the consistency of the point where I'm mapping my structure. So by the construction that I showed before, there would be some point in my space, so some vectors if I am in my vector space, and I'm looking at the agreement or disagreement of that with the probe that I want to use. Like, for example, this would be the case based on this type of a cosine similarity this is something that's actually commonly used in various settings of computational linguistics. So people use vector space models of semantics where you assign to words in general a vector where the coordinates depend on co-occurrences of your word with other words inside a corpus of text, for example. I'm mentioning these vector space models of semantics just not because they are particularly good models of semantics, but because they are very commonly used in computational applications, and they are simple. They're very commonly used because they are simple, but they are at least easy to describe. Okay, so now this means that the kind of setting we have is that we have a Hopf algebra. The Hopf algebra is the one that we use for the theory of merge. So it's the Hopf algebra of workspaces. And we're going to have some target Rota-Baxter semi-ring, which is built out of the semantic space and some kind of measurement of threshold of agreement and disagreement associated to that. And we can look at characters of the Hopf algebra with values in this target Rota-Baxter structure. And so there's one observation that is useful to make here is that this idea differs from several models of semantics that have been looked at in quite a lot in linguistics, in the sense that we're not requiring these targets to have the same kind of computational structure as their source. So a lot of, I mean, I will discuss some of them, later, probably next time, or some model of semantics that linguists have been looking at, they've been trying to reproduce the computational structure of syntax on the side of semantics. For example, there's one model that known as Piotrowski compositional semantics. And that is exactly trying to reproduce the operation of merge on the side of semantics by merging concepts, following the way that you merge structures on sentences. And so in that picture, the parsing of sentences in semantics is made out of reproducing the same operation of merge on the side of semantics. The pointed one, the lesson from physics here is that you don't have to do that. The computational side is all on the side of the combinatorics of this sort of discrete structure that is coming from the combinatorics. In the case of physics, it's the combinatorics of the Feynman graphs. And here is the combinatorics of the syntactic objects and workspaces that determines the structure of merge. The target on the semantic side does not have to have itself the same structure. This, in physics, the Feynman rules are not morphism of Hopf algebras. There's only a Hopf algebra on one side. On the other side, there is only this thing that separates out convergence and divergent part. There's no coproduct. So that you use the coproduct on the source and the Rota-Baxter operator on the target to make this factorization. But you don't have to have the same structure on both sides. And so that's, in a sense, something that I think is an advantage, because otherwise you kind of have to justify how the same structure comes up twice, once for syntax and once for semantics. You just have to have it once. Okay, so then if you have, so this is what happens in the case of physics. When you have something that's set up like this, you do have this possibility of splitting up your character into two parts. That one is sort of the part that you want and one is the part that you don't want. And if you think of this Rota-Baxter in our interpretation, as I said, this Rota-Baxter operator is like a threshold. So this would be the separating out the parts that meet the threshold and the parts that don't meet the threshold. And the way that you do separate out these two things is in this form that combines all the substructures into a single calculation. So this is telling you that you don't just check whether the entire structure meets the threshold or not, but you also check whether each of the substructure does. And somehow when you apply, what happens here, right, is that you recursively build this checking over substructures of what remains when you filter out by the threshold. So everything that's below threshold here will drop out, and everything that is above threshold will remain. And so then you look at the threshold of everything together, and so the only things that will remain at that point will be the ones where not just the entire structure, but all of its substructures and quotient structures separately will all meet the threshold. So they are the ones that have like the maximal parsing consistency, because all the substructure together survive. Okay, so and of course, this is all happening in this semi-ring target. And so your in a sense, I mean, here there's one point on how to keep in mind that the interpretation is slightly different from what is happening in physics. Here, you are really trying to detect where agreement and disagreement are happening over all substructures, and where consistency and inconsistencies are located in all your substructures. So the point is that you don't. I mean, the conceptual difference with respect to the case of physics, in this sense, this is more similar to the case of the theory of computable and non-computable function. In the case of physics, your goal is to modify your Lagrangian by the counter terms so that you will retain only the renormalized values of your Feynman item. So in the end, you want to modify your values so that you get the renormalized ones. Here, you don't have like a renormalized version of your sentence. It really that you want to be able to check, whether parsing works over substructures or not. Okay, so that's kind of the conceptual difference of interpretation. So let's come back to like our first example of the hexagonal republic. Right? Now you can think of what we were saying before. You can formalize it in this setting where you take the Boolean semiring, so the simplest possible case, the Rota-Baxter structure is just operator is just the identity. So all you're doing is to form this Bogoliubov preparation of your character. So your character is assigning truth values, meaning this structure parses okay or doesn't parse. This is like the simple 0-1 test. Then like something is awkward is 0, so everything is fine is 1. You don't put any intermediate values for that. And so you just look at what is the maximal agreements on all the possible substructure combined, and you will see that you read exactly the maximizers would be exactly the substructures that have consistent parsing. So the ones that are either this or that, and the part that drops out by the threshold is the part that actually contains the inconsistent. Okay, so now let's just look more closely at the case of the vector space model. Just as I said, not because it's a particularly intelligent type of semantics modeling, but just because it's simple and widely used. So let's again think about the fact, okay, we are in some the space S is just some vector space, and the probes are, well, we just choose some vectors and we measure agreement or disagreement with respect to the probe vectors that we've chosen. And again, okay, now these are our values, which are these inner products, are real numbers. So our semi-rings should have the real numbers as its elements, because that's where we evaluate. And we can also assume that, for example, if our structure does not have a well-defined head, then we throw it away, which means we declare it non-parsable, and we have this minus infinity value in the min plus semi-ring, and which just means we throw away things that are just non-parsable. Okay. So those are take value minus infinity. And if it is parsable, then you just compare it with the probe. So we have something that has values in this min plus, max plus semi-ring. And then we know that there we have an interesting threshold operation, which is this ReLU threshold. And so we can evaluate this factorization with respect to this ReLU threshold. And so what it's going to identify, the maximizers that we will obtain by that would be exactly those chains of nested subsequences where all of them have a positive, have agreement with the probe. And we will filter out anything that has an angle, larger angle that is disagreement with, that corresponds to disagreement with the probe. So of course, if I do it like this, right? For example, if I do it by using only the head of the tree as my measurement with respect to whether that is in agreement or not with the probe. Then I get something that's a bit too coarse, no, in the sense that it will not. So let me just put some simple examples. Just, if I make form a sentence, like this, and I can use probes. Like for example, I can see how certain other words can correlate in my semantic space. Remember that this kind of semantic spaces are based on measuring probability frequencies of co-occurrences of certain terms in a very large corpus of text. So of course, you expect that if I have a sentence like this, if I take some value that corresponds to words that have something to do with the notion of predator-prey or something like this, we'll have agreement with the several substructures in the sentence, and so we'll have a high correlation in these things. And you will be able to extract a chain of substructures where everything is consistent with the probe. And if I, of course, in this case, I would, in this simple example, I would be able to see the agreement even if I just focus only on the head of each subtree, and it would be enough to check this. Okay, and for example, if I change my my sentence by something that's now has some semantic, slice and more semantic disagreement between terms, then I would also be able to detect the disagreement with respect to the same probe that I used before. So I would detect that this change has changed the agreement disagreement with respect to a particular probe that I was using. And if you throw enough probes at something like this, we'll be able to see what changes where and what. So it's something that's kind of computationally implementable. If you have like a sample of probes over your dictionary or your semantic space. So, but for example, if you try the same thing with, again, our example of the hexagonal republic, if you only use the head of the tree, then that would not be enough information to see that there is the inconsistency. But if you use the actual location of the tree in these interpolations by geodesic arcs in the semantic space, then that would be sufficiently more information to be able to see the difference. So it's in a sense the better. This means that like the more you get embeddings of your trees inside your semantic space, the more this kind of probes will work better at parsing the semantic structure. And so I'm making this point actually because another thing that I will discuss a bit later is what happens now with the large language models. And you see that there one can also detect the fact that there is an embedding that is happening of syntactic structure inside some semantic space. And in a sense, there is a general question right now, which is how well these models capture the actual structures of language, beyond syntax that's sufficiently straightforward, but how well syntax is actually captured. And in a sense, this depends on how good this embedding is. And one can see already with making very simple examples here that the better your embedding is, the more you're likely to be able to give a good matching of syntactic structures and the corresponding parsings in semantics. So so this idea that you want to use not just the map of lexical items and but also this kind of geodesic interpolations between them as a way to form an embedding of syntax inside semantics allows it for a better parsing. Okay, so I'm gonna continue next time. I'll say a bit more about this kind of model of semantics next time.